Today we are going to discuss about synthesis of nanomaterials. Mainly three different types of methods have been discussed here: sol gel method, chemical vapor disposition, chemical reduction method. Before going into our topic, I would like to say what do you mean by nanomaterials. A nanomaterial is defined as a material which is synthesized with any of one parameter like length, breadth, area mentioned or maintained in a nanoscale. Whenever you go for a synthesis by nano approach, the material synthesized will be having different property than that of the bulk, like its thermal, catalytical, mechanical, optical, electrical, and all types of property would be altered by the synthesis of it in the nanoscale. There are mainly two types of approaches for synthesis of nanomaterial: top-down approach and bottom-up approach. The first method is top-down approach. Here we take a bulk material that is actually synthesized by a normal approach and we go for disassembling it. Then the bulk becomes powder and then further it is separated or disassembled to get the nanomaterial. The top-down approach is shown in the left side of this diagram. That's a bulk is converted to the powder and powder is converted to nanomaterial. The second approach is the bottom-up approach. It is exact reverse of the top-down approach. So here by synthesis we prepare an atom, that is the atom aggregate, or they grow and we call them as clusters. That is actually an assembly of particles or like atom, and then they will assemble further to give the nanoparticle. That is all about the bottom-up approach. The bottom-up approach is shown on the right side of this diagram, that the atom is converted to clusters, then the clusters is again converted to nanomaterial or the nanoparticles. This process could be visualized easily by this diagram. Next is also a diagram that shows about the top-down approach and the bottom-up approach, but additional points have given in this diagram. In top-down approach, it refers to slicing or successive cutting of a bulk material to get the nano-sized particle. That is, in top-down approach, the most of the time involves physical approaches like cutting, grinding, etc. But in bottom-up approach, it refers to a build-up of a material from the bottom, like atom by atom or a molecule by molecule. Atom by atom deposition leads to the formation of self-assembly of atoms or molecules or clusters. These clusters come together to form a self-assembled monolayers on the surface of the substrate. Going into our methods of synthesis of nanomaterials, the first method is sol gel process. First we look about what do you mean by sol and what do you mean by gel. A sol. A sol is a stable suspension of colloidal solid particle or polymers in a liquid. Gel is a porous, three-dimensional, continuous solid network which is surrounded by a continuous liquid phase. Therefore, the sol gel process is a wet chemical technique which is also known as chemical solution deposition and involves several steps in the following chronological order. The first step is hydrolysis, then polycondensation, gelation, aging, drying, calcification, crystallization, etc. Okay, next is sol gel process. Sol gel process we prepare most of the time as a metal oxide materials. The first step is hydrolysis, that is the formation of a stable solution of a metal alkoxide in water or a sol of metal oxide. It is done by hydrolysis in the presence of tetraethyl orthosilicate. The equation shows the hydrolysis step. MOR plus H2O gives MOH plus ROH. MOR is referred to as a precursor. Precursor means the starting reagent of a process. It's called as precursor. MOR means an alkoxide, metal alkoxide. That's a metal and an alkene group which is linked by an oxygen group. By hydrolysing the metal alkoxide, we get a solvated system, MOH, which is referred to as the sol. The second step is the sol of the metal oxide in water or dilute acid. It yields gel with the removal of liquid from the sol. This step, MOH, which is the product of the first step, react with the metal alkoxide again to get a product known as metal alkoxide gel, that is MOM. In this step, a sol is converted to gel. So this step is also known as polycondensation step. And once the gel is formed, the gel is then transferred to solid mass by the process synergesis. Synergesis means aging of the gel, or the solvent molecule is oozing out of the gel. Actually, this synergesis takes up to 7 days to happen. Next step is the drying of the gel. And by drying of the gel, it removes the last traces of water and the other volatile liquid that present in that gel. Next is the calcination of the gel, which is carried out at 800 degrees Celsius, and this calcination is done to stabilize the gel against rehydration, which produces the metal oxide with particle size falling in the range of nanoscale. This is a schematic representation of salt gel process. Here we take a precursor solution that is containing a metal alkoxide as a precursor. Then by continuous stirring and a hydrolysis and condensation, we get a gel, and the gel is again dried by evaporative drying or supercritical drying. We get a aerogel and aerogel. That is, the gel when dried in a supercritical drying, we get aerogel, and by evaporative drying or thermal drying, we get the aerogel and we get the final compound. This is a schematic diagram which represents the salt gel process. The next is also represents the revised version of salt gel process. Here we take the solution which undergo this hydrolysis to give the salt, and by gelation or condensation we get the gel. Then by supercritical drying we get an aerogel. The color is also mentioned here. Then by smettering heat in the same, we get a dense ceramic metal oxide nanoparticle. And but imagine that you have taken the gel from this step and you went for direct drying, you get a aerogel, and on grinding we get a powdered nanoparticle, that is this. Next, one more step is mentioned here, that from the salt also we can continue, that is a colloid. So here we take the colloid or the salt, this one, this is the salt or colloid. So from the salt or colloid also we can continue the step, that here to take the colloid or salt and go for spray, dip or spin coat, we get a dense thin film nanoparticle, or by drawing fibers we get a nanofibers out of it, and but the salt could also be directly dried to get the powdered form. So thereby in salt gel process we can prepare different types of nanoparticle, that is dense thin film nanoparticles, nanofibers have been prepared, powdered nanoparticles or dense ceramic nanoparticles can also be prepared. Next is the advantages and disadvantages of salt gel process. The advantages of salt gel process are: it's a simple, economic and efficient method, highly pure substances have been prepared from here, and uniform nanostructure, easily shapeable, low processing technique and control of dopant concentration. The disadvantages are high cost of fabrication, long period of deposition, not possible to attach thick layer of nanoparticles on the substrate, high temperature, that is 500 degrees Celsius required to form anodized nanopar crystals. The film is also very easy to agglomerate. The next step is the chemical vapor deposition. It's also known as CVD. It is a hybrid method, that is by using the chemicals in vapor phase for obtaining a coatings of variety of inorganic or organic materials. Under certain deposition conditions, the nanocrystalline films or a single crystalline films are being possible. Relatively, it has a simple instrumentation, it is an ease of processing, possibility of depositing different types of materials, and because of its economical viability, these are some advantages of CVD. And there are many variants of CVD like metallo-organic CVD, atomic layer epitaxy, vapor phase epitaxy, plasma enhanced CVD. These are all types of different variants of CVD. And these types of CVD differ from each other according to their source gas pressure, geometrical layout or temperature. Basic CVD processes can be considered as a transport of reactant and reactant vapor or a reactant gas towards a substrate which is kept at a high temperature, and then the reactant cracks into different products and diffuses on the surface and undergoes some chemical reactions at the appropriate site, and then undergo nucleation and then grow to form the desired material film. This is the process of chemical vapor deposition. and the byproducts are also be formed. These byproducts which is created on the substrate will be transported back into the gaseous form and then removed from the substrate. This is the schematic or the experimental setup showing chemical vapor deposition. That's a metallo-organic compound is used as a precursor, and the carrier gas here. This carrier gas is bubbled through a precursor at a room temperature, and the vapor stream is introduced into a control rate into a vacuum chamber via needle valve. These things are used for controlling the rate. Then the metal organic molecules then pass through a heated tube, and thermal decomposition of molecules takes place, forming small nanoparticles. That is, thermal decomposition of the molecules takes place at this furnace. Here the molecules are converted to small nanoparticles. Then the particles are condensed by using liquid nitrogen. In the cold fringer, we are using liquid nitrogen for condensing the particles, and then cooled and rotated, and the powdered forms samples are being collected or scraped off. It is the experimental technique of chemical vapor deposition. There are two ways, hot wall and cold wall, by which substrates are heated. In a hot wall setup, the deposition can be takes place even on reactor walls. This is avoided in cold wall design. Beside this, the reaction can take place in a gas phase with the hot wall design, which is suppressed in cold wall setup. And usually the gas pressures ranges from 100 to 10 raised to 5 Pascal. And the growth rate and the film quantity, it depends upon the gas pressure and the substrate temperature that we are using. It is the diagram which shows the cold wall and the hot wall. Next is the advantages and disadvantages of chemical vapor deposition. The advantages of CVD are high growth rate possible and can deposit materials which are hard to evaporate, good reproducibility and can grow epitaxial films, and for instance that metallo-organic CVD and also known as organometallic VPE, generally better films quality than PVD films. Disadvantages are high process temperature is used. It is actually a complex process. Toxic and corrosive gases are being used, and films sometimes may not be pure because of hydrogen incorporation. These are some advantages and disadvantages of chemical vapor deposition. Next, the third method, chemical reduction method. It is a widely used method, is the chemical reduction method. Here the nanoparticles are produced by the reduction of transition metals by using some reducing agents. The mainly used reducing agents are hydrogen, hydrazine, sodium borohydride, formaldehyde, ethanol, trialkyl borohydride. These are some reducing agents. And to prevent the agglomeration of metal particle, this synthesis is done in the presence of some stabilizers or the stabilizing agents like ligands like phenanthroline or polymers like PVP or surfactants like tetraalkyl ammonium salt. And by using anionic reductants as the reducing agent, we can prepare a most highly dispersed and a stable colloidal particles. It is the diagram showing the chemical reduction method. First, a metallic solution is taken in a salt solution is taken in a beaker, and it is heated, and then reducing agent is added. Then again heated, and the capping agent or stabilizing agent is added. Then again heated, and a metallic nanoparticles is prepared. Nanoparticles of different metals can be synthesized by chemical reduction method. In this method, a metal precursor solution such as metal salt solution is treated with a suitable reducing agent, then by appropriate stabilizing agents are added. After further treatment and drying, nanoparticles of metals are formed. These steps are exactly shown from this diagram. For example, synthesis of silver nanoparticles by chemical reduction method can be described as: silver nitrate solution is taken as a metal precursor, and hydrazine hydrate is used as a reducing agent, and sodium dodecyl sulfate and citrate of sodium are used as stabilizing agent. This reaction is carried out at room temperature and the transparent colorless solution is converted to a characteristic pale yellow and the pale red color. That is, it is the first one in the beaker. It is a pale yellow colored silver nitrate solution, and when it is stirred at a room temperature, the color changes from the pale yellow to pale red color, and the occurrence of the color indicates the formation of silver nanoparticle. These silver nanoparticles are then purified by centrifugation for 30 minutes, and to remove the excess silver ions, the silver colloids were washed at least 3 times with deionized water under nitrogen strain. Dried powder of nano-size silver can be obtained by freeze drying. The particle size of silver nanoparticle can be from 15 to 48 nanometer. That is the process of synthesis of silver nanoparticles by chemical reduction method. Aniline can be also used as a reducing agent, and copper nanoparticles can also be prepared by this chemical reduction method, in which the copper salt is used as the reducing agent, such as polyols, sodium borohydride, hydrazine, ascorbic acids are used as the capping agents. And chemical reduction method can be also used for preparation of different metal nanoparticles. That I have already said that it is a widely used technique. Next is the advantages and disadvantages of chemical reduction method. Advantages of chemical reduction methods are easy to perform, cost effective, efficient technique, and also allows the control of structural parameters through optimization of synthesis conditions. The disadvantages are the chemicals which are used in this chemical reduction method is costly and highly toxic, and therefore making them hazardous to environment. So these are the advantages and disadvantages of chemical reduction method. So we have discussed three methods: salt gel method, chemical vapor deposition, and chemical reduction method for the synthesis of nanoparticles. And these are some references that I have taken from. So thank you.